All right, folks, let's do the handshake problem. Imagine n+1 people. I know Josh Hutcherson, or whoever the guy's name is, was using n people, but let's now imagine n+1 people walking into a room one by one, where n is a positive integer. As each person walks in, that person shakes hands with each other person currently in the room. How many handshakes are there? Let's look at 3 ways to count them. All right. Method 1. Again, imagine n+1 people walking into a room one by one. So person number 1 walks into the room and has nothing to do. Let's say that this is the room. Here's the room. Person 1 has nothing to do. Waits for people to come in. But then person number 2 comes in and says hi to person number 1. Person number 2, person number 1, they shake hands. Then person number 3 comes in, shakes hands with both person number 2 and person number 1. Then person 4 comes in, shakes hands with person number 1, person number 2, person number 3. And so on and so forth. And then person number n+1 comes in. You can imagine them wearing jerseys with the number on them, right? Person n+1 comes in and shakes hands with the other n people in the room. 1, 2, 3, 4, and so forth. So what's a way of expressing the number of handshakes that take place? Well, person 2 shakes hands with person 1, that's 1 handshake. Person 3 shakes hands with 2 other people, 1 and 2, that's 2 more handshakes. Person 4 shakes hands with 3 people, that's 3 more handshakes, and so on and so forth. Again, person n+1 shakes hands with n other people. So this is one way of expressing the total number of handshakes. It's the sum of the first n positive integers. It looks pretty nice, but the problem is that ... the ellipsis. The problem is that this thing is not a closed form formula. There's a ... ellipsis thing in there. It's not a closed form formula. We would like a closed form formula for this. What is this equal to? The sum of a finite arithmetic series. What's this equal to? The sum of the first n positive integers. All right, let's look at 2 other methods for counting the total number of handshakes, because the numbers that we get, the expressions we get from all 3 methods should all equal each other. Let's go on to method 2. Imagine, once again, n+1 people in a room. So the people have entered the room. We have a room with n+1 people in it, and they've all shaken hands. Each pair of people have shaken hands. Let's say they've already done it. Okay, so here's the idea. Each of these n+1 people, let's say n+1 is 5 for now. Each of these n+1 people shakes hands with n other people. So if we have 5 people in the room, then each person has shaken hands with 4 other people. Right? But the problem is that if you look at it that way, this double counts, because we're counting person A's handshake with person B and person B's handshake with person A as different handshakes when we shouldn't be doing that. So we have to adjust for that double counting. So here's the deal. Person 1 shakes hands with the 4 other people in the room. Person 2, person 3, person 4, and here person 5. Okay. Person 2 shakes hands with, person 2 shakes hands with person 1, but we don't want to double count that, right? But shakes hands with 3 and 4 and 5. Person 3 shakes hands with person 1, but we've already counted that, and person 2, but we've already counted that. Person 3 shakes hands with 4 and 5. We've already counted person 4's handshakes with 1, 2, and 3. Person 4 only shakes hands with person 5. And by the time we get to person 5, we've accounted for all the handshakes. But once again, imagine the n plus 1, or in this case, 5 people in the room. Okay, n plus 1 is 5 in this case. Each of the n plus 1 people shakes hands with n other people. Each of these 5 people shakes hands, or they've shaken hands, with 4 other people. So each of the n plus 1 people has shaken hands with n other people. So we think there are a total of n times the quantity n plus 1 number of handshakes. But the problem is that along the way, we're double counting. If person 1 shakes hands with person 2, then person 2 has shaken hands with person 1 at the same time. So we're not supposed to double count this. This scheme up here double counts that. We don't want to count 1 shake with 2 and 2 shake with 1 as different handshakes. We want to count them as the same handshake. So we divide by 2. Because if you just take this product up here, you're double counting all the handshakes. We only want to count the handshake between 1 and 2 once. We only want to count the handshake between 3 and 4 once, and so forth. So the total number of handshakes is given by this, which is if you look at this geometrically, it's the total number of edges, these 5 edges here, the total number of edges, and also the diagonals in this n plus 1 gon. In this case, it's a pentagon. N plus 1 is 5. So again, the total number of handshakes equals the total number of edges and diagonals in this pentagon, this 5-sided polygon. In this case, n plus 1 is 5. Each of the 5 people has shaken hands with 4 other people. But we don't double count the handshakes. We only count the handshake between 3 and 4 and 4 and 3 as one handshake, for example. So right off the bat, my conjecture, my guess, is that the expression for method 1, the sum of the first n positive integers, 1 plus 2 plus 3 plus yada 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 plus n, I conjecture that this equals the fraction n times the quantity n plus 1 all over 2. For method 3, I'll show you a second way how we could have gotten this expression. Method number 3. Imagine the n plus 1 people in the room. Each pair of people shake hands. Now, how many ways are there to choose 2 people out of n plus 1 to shake hands? Basically, how many pairs of people are there in this group of 5? How many pairs of people are there? And each pair of people has shaken hands. Okay, well, we have 1 and 2, 1 and 3, we have 3 and 4, and so forth. N plus 1 choose 2. That's the number of pairs among the n plus 1 people. How many ways are there to choose 2 people out of n plus 1? You can also write this as n plus 1 C2, the number of combinations of n plus 1 people taken 2 at a time. And I claim that this equals that fraction that we saw from method 2. The same fraction as this fraction we got from the polygon approach, the total number of edges and diagonals. Now, this isn't as obvious, but look at my notes. Okay, it's explained in my notes. N plus 1 choose 2. If you write this in factorial form, it's n plus 1 factorial all over 2 factorial times, this turns out to be n minus 1 factorial. If you have n plus 1 runners in a race, 2 of them win, the other n minus 1 lose. Now, how do you simplify this factorial expression? This is great for the homework. Take the bigger factorial and start unraveling it until you get a great cancellation. N plus 1 all factorial, let's do the countdown. What are the factors here? We start with n plus 1. We count down. We then have n. And then we have n minus 1, yada, 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 all the way down to 1. But the product of all those will be n minus 1 all factorial, which cancels out, divides out completely with this guy down here. We get 1s here. So we're left with this simple expression, which we can, where we can switch around on top. Multiplication is commutative. We have n times the quantity n plus 1 all over 2 by working out this algebra very deeply. Same as what we got over here. In any case, my claim, my conjecture, is that this is true for all positive integers n. The sum of the first n positive integers, 1 plus 2 plus 3 plus yada 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 plus n, equals the fraction n times the quantity n plus 1 all over 2. And we're going to use mathematical induction as a means of proving this conjecture, this guess. Mathematical induction is used to prove conjectures or guesses, statements that we believe to be true, but are as yet unproven, even though you may have been convinced by my arguments. Now, unfortunately, the method itself will not give you this formula over here, okay? You have to arrive at it from your reasoning, like what we did with these three methods. For example, method 1 and method 2, or method 1 and method 3. Remember, method 1, okay, remember that method 1 gave us this, the sum of the first n positive integers, and then both method 2 over here gave us that formula, that fraction, and method 3 also gave us that fraction after some algebra, after a bunch of algebra. So we can conjecture this based on equating our expressions from method 1 and method 3, or from method 1 and method 2. Induction is then used to verify or prove our guess, our conjecture, and then we have a bona fide theorem. By the way, a fourth way you could have done this, if you remember arithmetic series, this is the nth partial sum of a basic arithmetic series. The formula for the nth partial sum can be found by using a formula we saw in section 9.2, and we arrive at this once again. Although we technically skipped that as we went through 9.2. That was optional. So really, 4 ways. There were 4 ways, at least, of figuring out or guessing this. And then finally, in our next videos, we're going to prove this using mathematical induction.